Hello, and welcome to another openFrameworks audio programming tutorial. Today, we will be building a wavetable oscillator. The advantage of a wavetable oscillator is that it is much more CPU efficient than calling sine each sample. We can look at a couple of benchmarks. In this test, sine took 14 times the amount of time to compute than the plus or addition, and in this other test, 60 times more. So there's a lot of factors at play that we don't have a lot of control over, considering what the compiler does, what operating system we're developing for, etc. But no matter what, calling trigonometric functions in the audio thread is best to be avoided whenever possible. Go ahead and do the usual thing. Start a new openFrameworks project. We don't need any add-ons at the moment. All right, so we're going to go through the normal motions. We'll need our exit function, our audio out, and let's go ahead and make a global sample rate and buffer size. So this will be the size of our audio vector. Okay, let's give this a quick test run. All right, so first let's build our oscillator from tutorial 1. This should be a lot quicker this time. We know we need a frequency, we need a phase increment, and we need a phase. We could use an amplitude, but we don't need to necessarily. All right, so let's set these up. Our frequency is going to be 440 to keep it classic. Our phase will start at 0. And our phase increment is equal to our frequency times 2 pi divided by our sample rate, which we will cast as a double. Let's make the order of operation clear. All right, and then we need to push this out. So we need to make a current sample equals the sine of phase. And let's multiply that by 0.05. Make it very quiet. All right, now we need to increment the phase. So phase plus equals phase increment. And then we need a, well, no, we don't. We could wrap that, do phase, if phase greater than or equal to 2 pi, phase minus equal 2 pi, but it doesn't matter if we're actually using the sine trig function, so we'll get rid of that for now. Buffer I times number of channels plus 0 for clarity equals current sample, and this is mono, so we'll have buffer I times number of channels plus 1 to address the second speaker and make it the same sample. All right, now we should have a 440 hertz sine wave. Okay, someone out there can do the math and make sure that was right. So that was a brief review of how we made a sine wave before. And the reason I put this in this tutorial is to point out the similarities of the two processes. All right, so for a wavetable, we'll need the size of a wavetable, which I'll make up here. And I'll make it fairly large, 2048 samples long. we'll need to actually make some storage for this table. So we can do, let's call it Wavetable. So we'll make that a pointer to a float. And in our setup, we'll have to allocate that space. So our Wavetable equals new float array of table size, which is 2048. All right, so now we have an array of 2048 floating point values. Over those 2048 values, we need to store one period of a sine wave. So we need to loop through every point of that array. So for this, we'll use a for loop. All right, and then we'll need to address the wave table at this index. So we'll go through every one. Equals sine of theta, which we don't have yet. All right, so we need to go from I, which is 0 to 2047, and convert that from 0 to 2 pi. So we can do float theta. And since we're in openFrameworks, we can use a convenient mapping function of map I from 0 to table size, map that to 0 to 2 pi. Okay, so this will work. Another way we could do theta is theta equal, let's see, divided by table size, and we could do I times 2 pi if we wanted to do this without the mapping function. Should give us the same result. Okay, so since we're in openFrameworks, we might as well visualize this waveform. There's a handy mesh wrapper in openFrameworks called of polyline. We'll call it waveform. There we go. No capital L in polyline. All right, so every time we go through the update function, we'll clear this. So waveform.clear, and then we'll repopulate. This way, if we resize the window or if we change the waveform, it will update. So for int I equals 0, I is less than table size. We'll make an x value. So x will be of map I from 0 to the width. Sorry, to the table size, to 0 to width. And our y value of this mesh will be whatever's in that table. So we can access our wave table at that index. And then we'll be at -1 to 1, since it's an audio storage. And then we'll map that to the height, which is the bottom of the screen, and then the top of the screen. All right, so now we can add a vertice for each of those audio points. So waveform.add vertex x, y. So that's updating every frame, and now we can just draw it. All right, so now when I run this, we shouldn't hear, well, let's get rid of this. And now we should see a sine wave on our screen. No. Okay, so I forgot the brackets here, or parentheses. strange. Okay, so I had that map to do the width instead of the height. Okay, so this visualization will be pretty handy in the next tutorial when we start adding harmonics to this. But there we can clearly see we have a sine wave. So let's try to run through this sine wave. So before we had our phase increment, and we had our phase, and it's not going to be much different now. Instead of going from 0 to 2 pi over a period, we're going to go from 0 to the table size over a period. And that's going to have a few implications. One variable that's new we'll need is table fundamental frequency. It's a strange concept, a strange idea to say that a table has a fundamental frequency, but we'll get to that in a second here. So the fundamental frequency is the frequency that would be present if we went through sample by sample. So if each time we had a new sample, we jumped to the next point of the table, what frequency would that be? So we can calculate that. We have a sample rate of 48,000 samples per second. We need to divide that by our table size. So if we jumped sample per sample, one entry per sample, then the fundamental frequency is 23 hertz. So we need to reference our phase increment value on this. So first we need to store this value, 23. So we'll have our table fundamental frequency equals our sample rate divided by our table size, cast as a double. I suppose we could cast it as a float. It will be truncated anyway. All right, so our fundamental frequency is there. So now for our phase increment, we need to do phase inc equals our frequency divided by our table fundamental frequency. And that's all we have to do. So now instead of incrementing by a portion of theta, we're incrementing by a portion of the table. So now our current sample is going to be our wave table at phase. And this will be a little problematic, and this will be unhappy here. Our phase is a float. This is going very slowly today. But our phase is a float. We can't access an array at a floating point value. We have to access an integer. So I'm going to go ahead and cast this as a float, or as an integer, sorry, to make it happen and make it compilable, but we'll have to do some adjustments there. All right, and as before, our phase plus equals our phase increment. All right, this time our table is finite. It's not like sine where we can go over 2 pi and it's going to solve that for us. We need to make a wrapping function. So if our phase is greater than or equal to table size, we need to subtract the table size. Phase minus equals table size. This is the same as saying phase equals phase minus table size. All right, so that'll wrap it back around appropriately. Let's make sure everything's right. So our phase is starting at 0. Our frequency is 440. So now we should have something that resembles loosely a sine wave. I'm going to stop it because I never turned it down. You are very welcome. Let's turn this down a bit, or a lot. There we go. Oh man. Something is horribly wrong. Okay, so what happened is we have a double set of this. So our phase increment is actually very slow compared to what it needs to be, since we reset it there. Great, and that was loud again. Okay, so we have our sine wave. So let's do a couple things to test out the sine wave. Let's assign the frequency to our mouse x. And the way I like to do it is exponentially. So we can say float octave equals of map. We'll map x from 0 to the width of the screen to, let's say, 4.5, actually 4, and 14.5. So this will cover the whole range of human hearing. And then our frequency is going to equal the power of 2 to the power of our octave. So this will give us about 16 to around 22K, I think. And then if we change frequency, we'll also have to change the phase increment, because we're not actually using frequency in our audio thread. So phase inc equals, I believe it was frequency divided by our table fundamental frequency. All right, so now we can change the frequency. All right, so if you're listening with headphones, you can hear a lot of truncation noise, especially in the low end. Additionally, we have the problem of the stepping noise when we move pixels. Since pixels are integers, we need to move smoothly between them. Fortunately, we've solved that problem before. Let's add our audio tools file to this project. I will have these linked in the description, I promise this time. I happen to have mine on the desktop, so we can just drag these on in here. I'll include them in the header. All right, so let's change frequency to a smooth value. And make the necessary adjustments. So frequency target value equals 440. Frequency current value is equal to the same. And then set our smoother. I think I called it parameter smoother. With the fields milliseconds, let's do 1,000, full second lag, and sample rate. All right, that looks happy. And then we need to adjust this because frequency is pointing to a data type now, or a different data type. So we'll set this to current value. And then when we move the mouse, we need to change the target value. All right, and then this adjustment will have to happen in our audio thread. So our frequency current value is going to determine our phase increment size. And lastly, we need to adjust our current value. So frequency current value is equal to our smoother, and we'll get the sample. See, process frequency dot target value. All right, it's a bit to type, but it keeps it all related. All right, so now when we move the mouse, we should have smooth movement, so we can hear only the truncation noise. Okay, so it's definitely a sine wave. It's just a lot of noise happening for that. And fortunately, this is a problem we've already solved before. We just need to add some linear interpolation, and that will take care of that. So in the audio programming book, they call this a guard point. We're actually going to add an extra point to the end of the array so we don't have to do a wrapping function for the index, which will save us some processing time. So our table is 2048 samples long. Let's actually decrease how long it thinks the table is. So we're going to do table size -1 here, and then we'll keep our table size the same size. All right, so this will start our sine wave over one sample at the end. Let's make sure this is still right. This won't make a huge difference in the visualization since we have to ignore some anyway, but might as well adjust it. So if we need to change this and this. I'll put parentheses here so the order of operation is clear. Okay, so now we've decreased our actual sine wave period by one sample so that when we get to the end, we can look at the next sample without having to wrap our index in our linear interpolation function. So let's add our linear interpolation. So our current sample is going to be the linear interpolation of our wavetable at the truncated version of our phase. So that's the first point, and then our wavetable at the truncated version phase +1. So these will be the surrounding indices, and then we need to give it our position between these two indices by giving it phase. Okay, so I'm going to move this aside here. I guess I'm not. Okay, so our linear interpolation, our first point and our second point, how far are we between those 2 points? And this will return our linearly interpolated value. I'll move the amplitude adjustment to a separate line, so our current sample times equals 0.1. Make it a little louder this time so we can really hear some noise if there is some. All right, and that should do it. Let's have a listen. All right, that sounds, I don't hear any, I'm using earbuds at the moment. Maybe if you have a higher quality DAC and headphones, you might be able to pick up some noise. It would sound better to use cubic interpolation, but linear is just fine for this purpose. All right, one thing we have not covered for wavetables is how to normalize wavetables when we use additive synthesis and how to adjust per octaves. Since you have a varying number of harmonics, depending on which octave you are for a square wave or a triangle wave, a varying number of audible harmonics, I should say, some of those harmonics will be past the Nyquist frequency. And that is a huge problem. Those will fold back in non-harmonic ways. This is a form of aliasing. And additionally, when you use a wavetable, you're adding a whole new set of aliasing, since you can actually alias your table before you even play that table back. So we're going to be covering some more complicated topics in wavetable synthesis in the next tutorial. Thank you.